After studying this module, you shall be able to know about infrared spectroscopy, the instrumentation required for infrared spectroscopy, the applications and limitations of IR spectroscopy. Introduction. The infrared region of electromagnetic spectrum extends from the red end of visible spectrum to the microwave region. The region includes radiation at wavelengths between 0.7 and 500 micrometer or in wave numbers between 14,000 and 20 centimeter inverse. The spectral range used most is the mid region, which covers frequencies from 4000 to 200 centimeter inverse, that is from 2.5 to 50 micrometer. Infrared spectrometry involves examination of the twisting, bending, rotating and vibrational motions of atoms in a molecule. Atoms or atomic groups in molecules are in continuous motion with respect to one another. Atomic masses are represented by balls. Their weights being proportional to the corresponding atomic weights are arranged in accordance with the actual space geometry of the molecule. Mechanical springs with forces that are proportional to the bonding forces of the chemical links connect and keep the balls in balance. If the model is suspended in space and struck, the ball appears to undergo random chaotic motions. Correlation of infrared spectra with molecular spectra. The infrared spectrum of a compound is basically the superposition of absorption bands of specific functional groups, yet slight interactions with the surrounding atoms of the molecule impose the stamp of individuality on the spectrum of every compound. For qualitative analysis, one of the most excellent feature of an infrared spectrum is that the absorption or lack of absorption in specific frequency regions can be correlated with specific stretching and bending motions, and in some cases with the relationship of these groups to the rest of the molecule. Thus, when interpreting the spectrum, it is probable to state that certain functional groups are there in the material and certain others are missing. With this one datum, the possibilities for the unidentified occasionally can be narrowed so sharply that comparison with the library of spectra of pure compounds permits identification. Near infrared region. In the near infrared region, which meets the visible region at about 12,500 centimeter inverse and extends to about 4,000 centimeter inverse, there are numerous absorption bands that results from harmonic overtones of fundamental and combination bands often associated with hydrogen atoms. Among these are the first overtones of the OH and NH stretching vibrations near 7,140 centimeter inverse and combination bands that results from CH stretching and deformation vibrations of alkyl groups at 4,548 centimeter inverse. The absorptivity of NIR bands is from 10 to 1000 times less than that of mid-infrared bands. Thicker sample layers compensate for these smaller molar absorptivities. Because the absorptivities are so low, the NIR beam penetrates deeper into a sample in reflectance techniques, giving a more representative analysis. Furthermore, minor impurities are less troublesome in both reflectance and transmission methods than in the mid-infrared region. The NIR region is accessible with quartz optics, and this is coupled with greater sensitivity of near infrared detectors and more intensive radiation sources. The near infrared region is often used for quantitative work in addition to qualitative identification. Near infrared spectrometry is a valuable tool for analyzing mixture of aromatic amines. Primary aromatic amines are characterized by two relatively intense absorption bands near 1.97 and 1.49 micrometer. Secondary amines exhibit and overtone band but do not absorb appreciably in the combination region. These differences in absorption provide the basis for rapid quantities analytical methods. Tertiary amine do not exhibit appreciable absorption at either wavelength. The overtone and combination bands of aliphatic amines are shifted to about 1.525 and 2.00 micrometer respectively. Interference from first overtone of the OH stretching vibration at 1.40 micrometer is easily avoided with the high resolution available with near infrared instruments. Near IR reflectance spectra find wide acceptance in the food and grain industry for the determination of protein, fat, moisture, sugar, oils, iodine number and so on. NIR reflectance spectra have also been used for the determination of substances in wood, components of polymers and even geological exploration from aircraft. The method is fast and useful in routine analysis. For substances, sample preparation is extremely simple. The sample is merely poured into a cell and inserted into a sample chamber of the instrument. The NIR reflectance method really depends on pattern recognition by the computer, and if there are unexpected substances in the unknown, false determination can be made. Mid-infrared region. Numerous practical correlations have been found in the mid-infrared region. This region is divided into the group frequency region, that is from 4000 to 1300 centimeter inverse, and the fingerprint region, which is from 1300 to 650 centimeter inverse. In this group frequency region, the main absorption bands are assigned to vibration units consisting of merely two atoms of a molecule, that is, units that are more or less dependent on only the functional group that gives the absorption and not on complete molecular structure. Structural influences do reveal themselves, however, as significant shift from one compound to another. In the derivation of the information from an infrared spectrum, prominent bands in this region are noted and assigned first. In the interval from 4000 to 2500 centimeter inverse, the absorption is characteristic of hydrogen stretching vibrations with elements of mass 19 or less. The CH stretching frequencies are especially helpful in establishing the type of compound present. For example, CC double bond CH occurs around 3300 centimeter inverse. Aromatic and unsaturated compounds around 3000 to 3100 centimeter inverse, and aliphatic compounds at 3000 to 2800 centimeter inverse. When coupled through heavier masses, the hydrogen stretching frequencies overlap the triple bond region. The intermediate frequency range, that is from 2500 to 1540 centimeter inverse, is often called the unsaturated region. Triple bonds or very little else appear from 2500 to 2000 centimeter inverse. Double bond frequencies fall in the region from 2000 to 1540 centimeter inverse. By careful application of accumulated empirical data, it is possible to differentiate among C double bond O, C double bond C, C double bond N, N double bond O and S double bond O bands. The major factors in the spectrum between 1300 and 650 centimeter inverse are single bond stretching frequencies and bending vibrations of polyatomic system that involves motion of bonds lining a subsequent group to the remainder of the molecule. This is the fingerprint region. Multiplicity is also great for certain individual identification of the bands, but together the absorption bands aid in identifying the material. Far infrared region. The region from 667 to 10 centimeter inverse contains the bending vibration of carbon, nitrogen, oxygen and fluorine with atoms heavier than mass 19, and additional bending motion in cyclic or unsaturated systems. The low frequency molecular vibration in the far infrared are predominantly sensitive to changes in the overall structure of the molecule. Thus, far infrared bands often differ in a way for diverse isomeric forms of similar basic compounds. The far infrared frequencies of organometallic compounds are usually sensitive to the metal ion or atoms, and this too can be used advantageously in the study of coordination bonds. Moreover, this region is particularly well matched to the study of organometallic or inorganic compound whose atoms are heavier and whose bonds are inclined to be weak. Instrumentation. The usual optical materials, glass or quartz, absorb strongly in the infrared region. Consequently, the apparatus for measuring infrared spectra is appreciably different from that for the visible and UV regions. The main parts of an IR spectrometer are the IR radiation source. In common with other types of absorption spectrometers, infrared instruments require a source of radiant energy which provides a way for isolating narrow frequency bands. In case of IR spectrometers, the source of radiation should be such that it is intense enough for detection, extends over the desired wavelength and is steady. Although these radiations are continuous, only selected frequencies will be absorbed by the sample. The various popular sources of IR radiations are incandescent lamp, Nernst glower, globar source, mercury arc. Monochromators. The radiation source emits radiation of various frequencies. As the sample in IR spectroscopy absorbs only at certain frequencies, it therefore becomes necessary to select desired frequencies from the radiation source and reject the radiation of other frequencies. This selection has been achieved by means of monochromators, which are mainly of two types, prism monochromator and grating monochromator. The next component is sample cell and sampling of substances. As infrared spectroscopy has been used for characterization of solid, liquid or gas samples, it is evident that samples of different phases have to be handled, but these samples have to be treated differently. However, the only common point to the sampling of different phases is that the material containing the sample must be transparent to IR radiation. We will now discuss the sampling of solids, liquids and gases separately. First, we will see sampling of solids. Samples that are solid can be sampled as solid run in solution, solid films, mull technique and pressed pellet technique. Sampling of liquids. The sample that are liquids at room temperature are usually put frequently with no preparation into rectangular cell made of NaCl, KBr or THBr, and their IR spectra are obtained directly. Sampling of gases. The gas sample cell is similar to the cell for liquid samples in as much as the surface in the light path are made of KBr, NaCl and so on to compensate for small number of molecules of a sample that is contained in a gas, however the cells are large. Usually they are about 10 cm long, but they can be up to 1 meter long also. The gas must not react with the cell windows or reflecting surfaces and moisture must be avoided. The next component is detector. Excluding the near infrared where the photoconductivity cell is generally used, there is no better choice than the thermal detectors. These gives response for all frequencies when the radiant power is low for infrared region. It means that the detector signal will also be low. In order to locate these frequency, light interrupter 10 to 26 CPS is used. Thus, to detect such signal, thermal detectors must possess a short response time and absorbed heat must be lost rapidly. The latter condition is a most difficult requirement because heat transfer is not a quick process. The various types of detectors used in IR spectroscopy are bolometers, thermocouple, thermistors, Galois cell, photoconductivity cell, semiconductor detectors, pyroelectric detectors, Fourier transform systems, Fourier transform infrared spectrometer, FTIR. Infrared radiation can be analyzed by means of scanning Michelson interferometer. This consists of a moving mirror, a fixed mirror and a beam splitter. The moving mirror collimates the radiation from IR source and the resultant beam is divided by the beam splitter. Half the beam passes to a fixed mirror and half is reflected to the moving mirror. The two beams recombine at the beam splitter after getting reflected and interfere constructively or destructively for any specific wavelength subjected to the difference in optical paths between the two arms of the interferometer. With a constant mirror velocity, the intensity of emerging radiation at any particular wavelength modulates in a regular sinusoidal manner. In the case of a broadband source, the emerging beam is a complex mixture of modulation frequencies that, after passing through the sample compartment, is focused onto the detector. This detector signal is sampled at precise intervals during the mirror scan. Both the sampling rate and the mirror velocity are controlled by a reference signal incident upon a detector, which is produced by modulation of the beam from the helium neon laser. The resulting signal from detector is known as an interferogram and contains all the information required to reconstruct the spectrum via mathematical process known as Fourier transformation. This technique has several distinct advantages over the conventional dispersive techniques. There is only one moving part involved, one of the mirror mounted on a frictionless air bearing. Dispersion or filtering is not required, so that energy wasting slits are not needed. This is a major advantage, particularly with energy at a premium in the far infrared, and the use of a helium neon laser as a reference results in near absolute frequency accuracy, better than 0.01 centimeter inverse over the range of 4800 to 400 centimeter inverse. The interferogram recorded with each scan is stored in memory. This interferogram is then automatically aligned with and added to the average interferograms in another memory. At the same time, annotation of the plot is begun in preparation for the final spectrum. After a number of scans, often 32, this average interferogram is Fourier transformed to produce a single beam spectrum, which in the standard sample mode is stored in third memory. This single beam spectrum is then ratioed against the stored background in fourth memory, and the resulting double beam spectrum is plotted on the high speed digital plotter. Memory 5 is additional space available for storage of a reference spectrum that would be used in the spectral subtraction technique. This memory is also used to store a newly measured spectrum while maintaining the sample and the background spectra for further manipulation. The time from insertion of the sample to the completed plot is about 2 minutes. Since the computer uses digital data, the photodetector signal must be converted to digital form by an analog to digital converter. The data must be sampled at precise points and the resultant data stored. Fourier transform infrared spectrometers are still more expensive than sequential dispersive instruments due to the precision needed for mirror movement and the computer that is also required. However, dispersive instruments are now often equipped with computers that can record and remember spectra, plot absorbance, transmittance or some functions of absorbance, subtract one spectrum from another and do other functions, and this adds to their price. The power of FTIR instruments has led to much competition in the instrumentation industry, resulting in an increased availability of commercial instruments and a decrease in price. Low-cost FTIR instruments are beginning to appear. Fourier transform spectrometers are faster than dispersive instruments and therefore and especially useful in situations that require fast repetitive scanning. They are used in recording the output of gas or liquid chromatographs or obtaining kinetics data. Application of infrared spectroscopy. Identification of organic compounds. The infrared spectrum is highly characteristic property of a substance and the examination of infrared spectrum can aid chemical investigation in many ways. The important application of infrared spectroscopy is given as follows. Identification of substances such as hydrocarbons like alkanes, cycloalkanes, aromatic hydrocarbons. Identification of substances such as hydroxy compounds like alcohols and phenols. Identification of substances such as aldehydes and ketones, carboxylic acids, carboxylic acid derivatives, amines and nitro compounds. Determination of molecular structure. Infrared spectroscopy is extremely helpful in determining the molecular structures of unknown substances. From an assessment of the position of absorption bands in the spectrum, it is often possible to establish the nature of groups present in the molecule. Studying the progress of reactions. Progress of chemical reactions can be readily followed by examining the spectra of small portions of reaction mixture withdrawn from time to time. Next is detection of impurities. It is likely to determine whether a given sample of a compound is pure or not, provided the reference spectrum of a pure compound is available. Isomerism in organic chemistry. IR spectra are useful for identifying isomers. This distinction between isomers may not be possible by chemical methods. Geometrical isomerism. In general, trans isomers are more symmetric than cis and consequently the vibration of the former give rise to little or no change in dipole moment. Tautomerism. Application in inorganic complexes. Miscellaneous examples. The following are some important applications which give important clues to the structure of coordination compounds. This also includes an application which is used to detect the presence of an impurity in an organic compound. Determination of purity. Infrared spectroscopy has been used for establishing the purity of compound. Whenever a compound is having an impurity, it reduces the sharpness of individual band, causes the appearance of extra bands and a general blurring of the spectrum. Shape or symmetry of the molecule. IR spectra can be used to deduce the shape or symmetry of the molecule. This can be illustrated by considering the example of nitrogen dioxide. Presence of water in a sample. If the sample contains lattice water, its IR spectrum will contain three characteristic bands. One in the range of 3600 to 3200 centimeter inverse, second in 1650 centimeter inverse region and third in 600 to 300 centimeter inverse region. Measurement of paints and varnishes. Frequently paints and varnishes are measured by reflectance analysis, a process where the sample is irradiated with IR light and the reflected light is introduced into an IR instrument. Examination of old paintings and artifacts. Another interesting application is the examination of old paintings and artifacts. It is possible to identify the varnish used on the painting and the textile comprising the canvas as well as the pigments in the paints. In industry, IR spectroscopy has three important uses. First, it can be used to determine impurities in raw material. This is necessary to ensure good products. Limitations of IR spectroscopy. Although IR spectroscopy has proved to be one of the most valuable methods for characterizing both qualitative and quantitative the multitude of inorganic compounds encountered in research as well as in industries, yet it suffers from some shortcomings which are outlined by IR spectroscopy. It is not possible to know molecular weight of a substance. Generally, the IR spectroscopy does not provide information of the relative position of different functional groups on a molecule. From the single IR spectrum of an unknown substance, it is not possible to know whether it is a pure compound or a mixture of compounds. An interesting example is that a mixture of paraffin and alcohol will give the same IR spectra as by higher molecular weight alcohols. It should be pointed out, however, that with prior knowledge of the components of a mixture and their spectra, Many analyses of mixtures are performed daily by IR spectroscopy, which despite these shortcomings has proved to be one of the most valuable methods for characterizing both qualitatively and quantitatively the multitude of organic compounds and mixture of compounds encountered in research and industries. Now let us summarize. The infrared region of the electromagnetic spectrum extends from the red end of the visible spectrum to the microwave region. The infrared spectra consist of near infrared spectra, mid infrared spectra and far infrared spectra. The infrared spectroscopy instrumentation includes the IR radiation source, monochromators, sample cells and sampling of substance, detectors. The application of infrared spectroscopy include identification of organic compounds, determination of molecular structure, studying the progress of reaction, detection of impurities and isomerism of organic chemistry. The applications also include the determination of purity, shape and symmetry of the molecule, presence of water in sample and many more. Although infrared spectroscopy has lot of application, it also has many limitations.